Alright, so I gave in. Fourth video, and we have the position function down here. We're going to do example 6. We're going to skip example 5. If you look down at the bottom of your page, you should see a page 78. This is our final video. So example number 6, we're given that a rock is thrown vertically upward from the surface of the moon at an initial velocity of 24 meters per second, and it gives the height in terms of meters in t seconds. Okay, so we're supposed to find a bunch of stuff about this particular example. First thing is the rock's velocity and acceleration as a function of time. So we already know how to do that. Oh, by the way, I would encourage you to pause the video and try this on your own before you watch the video. Rock's velocity as a function of time would be the derivative of the position, 24 minus 2 times 0.8 is 1.6 t, and then the acceleration at time t would be negative 1.6. Well, remember, the acceleration on the moon, or maybe you didn't know this, the acceleration on the moon would be it's about a sixth. Well, I know the gravity on the moon is about a sixth of the gravity on the as that on the Earth, so there's got to be something in there on that acceleration. So it would be less on the moon than it would be here. Acceleration due to gravity. So how long did it take the rock to reach its highest point? Well, we need to figure out when it reaches its highest point. Remember, velocity is positive on the way up, negative on the way down, but 0 right there at the highest point. So we're going to set v of t equal to 0, and we're going to solve for t. So 24 minus 1.6 t is equal to 0 when 1.6 t is equal to 24. And so t, if you did 24 divided by 1.6, and I don't want to make any mistakes by trying to do this too much in my head, so t equals 15. Okay, t equals 15. How long did it take? And that would be 15 seconds. Okay. Wow, you didn't even see it. Sorry. So t equals 15 seconds, and I'll pause there where you can look at that. V equals 0. When the velocity equals 0, solving this equation for t, we find that t is equal to 15 seconds. And how high did the rock go? Well, if we want to know how high the rock went, and remember this is on the moon. You throw a rock up into the air, it takes 15 seconds to reach its highest point. So that's kind of an interesting thing. How high did the rock go? Well, that's the position at 15, and the position at 15 would be 24 times 15 minus 0.8 times 15 squared. And what is that? Let me do this. Let me clear that. And we get 24 times 15 minus 0.8 times 15 squared. And that's 180, it's not feet, is it? It's meters. 180 meters. Okay, so if you throw a rock up into the air on the moon, it's going to go 180 meters up above you. So part B, how long did it take the rock to reach half its maximum height? Okay, so we want to know how long it took the rock to reach half. We want to know what the position, so the position is equal to, when the position is equal to half its maximum height, so 90 meters. When that equals 90 meters, then 24t minus 0.8t squared is equal to 90. Solving this equation for t, we're gonna let's see. Let's go ahead and bring the 90 over to this side. So we have negative 0.8 t squared plus 24t minus 90 equals 0. And that's a quadratic equation, and we're going to go ahead and solve that quadratic equation using our... Oh man, this calculator doesn't have quadratic formula. Oh, what a disaster. Oh, this one does. Cool. So we've got, enter the coefficients, negative 0.8 for A, and then for B it's 24, and for C it's negative 90, and we've got S of t equals 90 when t equals 4.393, and also 25.607. Well, guess what? It hits 90 meter mark on the way up at 4.393. Keep doing that. 4.393, and then on the way down at the 25.607 seconds mark. And so that's how we interpret that. So on the way up and on the way down, it hits a position of 90 meters. How long was the rock aloft? Well, how long was the rock aloft would be, what do we have to solve for? Well, what do we want to know? We want to know S of t. It took 15 seconds to reach the height surface of the moon. So if it took 15 seconds to get up, then it's going to take 15 seconds to come back down, and so we would say 30 seconds. Well, okay. So when the position is 0, S of t equals 0 when 24t minus 0.8t squared is equal to 0. So we can solve that for t, and we would find that t equals 0 and t equals 30. Okay. And then the rock's speed when hitting the moon. Alright, so part E, last part. The rock's speed when hitting the moon at t equals 30, we want to know the speed. So first let's find the velocity. Actually, let's just go ahead and go right to the speed. The absolute value of velocity at 30 would be the absolute value of 24 minus 1.6 times 30, and that would be 24 minus 1.6 times 30, and that's going to be the absolute value of negative 24, which is 24. And what would the speed be? It would be meters per second. So just like we saw in the last example, the speed at which whatever's being thrown up into the air, shot up in the air, leaves is the speed that it hits the ground. Okay? And we're at 7:25 here. Maybe we'll be able to squeeze in these last couple examples. A ball is dropped from the top of the Washington Monument, which is 555 feet high. How long will it take the ball to hit the ground? Well, the initial position is 555, and we have an initial velocity of 0. So the position then is, feet would be negative 16t squared plus 555. So the only thing affecting this the speed or the location of this particular ball would be gravity, because you just drop it right off the roof. Okay, roof or top of the Washington Monument. So how long will it take for the ball to hit the ground? Well, S of t equaling 0 would be the position of the ball when it's on the ground. If we want to know how long it takes that to happen, then we would set S of t equal to 0. So we have negative 16t squared plus 555 equals 0 when 16t squared is equal to 555. And let's use our calculators for that. We would come right up here and we'd get t squared equals 555 over 16. And we're going to need to take the square root of that. Square root of 555 divided by 16. And that's going to give us 5.8896. So 5.89 t equals 5.89 seconds. Okay, well that's how long it's going to take the ball to hit the ground. Find the ball's speed at impact. Well, the ball's speed at impact will be the velocity at that time, 5.89. By the way, you're going to want to store that in A on your calculators. Let's get you over here. Store that in A. So I'm going to do that. Store alpha A. And then I want to figure out, well, the velocity at 5.89 is, where's the velocity? It's negative 32t. Okay. When t is 5.89. I should put an A right there. So the absolute value, math, right arrow, enter. Absolute value of negative 32 times a would be, I don't need that anymore, would be equal to 188.468, and that would be meters per, no, I guess that's feet per second. Yeah, feet per second. Okay, there you go. 188.468 feet per second. So hopefully you're getting these answers, same ones, and I am going to do this. I wish I could pause this. That would be really kind of cool. I could pause my computer. I can't do that. So I guess you're just going to have to listen to me ramble a little bit. Let's see how far we can get for this particular problem. Paul has bought a ticket on a special roller coaster at an amusement park, moves on a straight line. Position of the car in feet after t seconds is given as this for 0 to 120. So for the first 2 minutes, okay, velocity and the acceleration of the roller coaster after t seconds. Well, the velocity is the derivative of the position, and 3 times 0.01 would be 0.03 t squared, and then 2 times 1.2 would be 2.4 t. Okay, and the acceleration then would be 2 times negative 0.03 would be negative 0.06 times t plus 2.4. When is the roller coaster stopped? So part B, when is it stopped? Well, that's when the velocity is 0, when the negative 0.03 t squared plus 2.4 t equals 0. Now, I would put this into the calculator, so let's do that. Let's see how much time we have left. 3 minutes, so we'll do our best. And again, we're going to take our get into function mode, and we're going to type in negative 0.03 x squared plus 2.4x. Okay, and we can only x here in this case on the calculator is our t value, and let's let that be up to 6, and I don't know what y is going to be, but it doesn't really matter. Negative 10 to 10, and so we have, that's our velocity, and our velocity at 0. Well, solving this, I guess we could use our program quad. And our program quad, our a value would be negative 0.03, and our b value would be 2.4. Enter, and the c value would be 0. So we get 0 and 80. So the velocity is 0 when t is equal to 80 seconds. Okay, so t is equal to 80 seconds. That's when the roller coaster stops. And speeding up and slowing down. So the bottom line is, oh, that's good. That's a good question. When is it speeding up and slowing down? Well, I guess from this we can see that our window needs to be past x max of 80, so 120. So let's see what the graph looks like. We're going to need a higher y, so let's let that be 100. And then we're going to need a lower y. Let's let that be negative 100. Let's see what that does. Okay, so maybe a little bit lower, so negative 200. So basically, there we go. This is the graph of the velocity. The velocity is positive between 0 and 80, and it's negative from 80 to 120. Okay, so in other words, at the 80-second mark, this guy in the roller coaster stopped and then started going back to the left. Okay, roller coaster moves in a straight line. Paul is speeding up, so the velocity is positive on 0 to 80, and the velocity is negative on 80 to 120. Okay, I've got 15 seconds left, so I might not be able to get to the rest of this. Speeding up and slowing down, so acceleration at, man, not going to be able to do it. So I'm going to leave C and D to you guys. I can't finish this by 15 minutes.